All right, well, that's that. So we basically covered all of 7.5 on the trig equation stuff last time. If you remember, we were solving things like this. Remember, we have to map out, our equations. There are a couple of examples that I didn't do. Namely, like example 14 and example 15. I didn't do that last time, but we've done all the way through example 13. Right, that one. Okay. By the way, 14 is very, very similar to that example 13, except for I want to point out, well, I guess I'll just go ahead and do example 14. Here we have cosine of 2 theta. Plus 13 times cosine of theta. Minus 6 is equal to 0. So the first thing that you should look at that and see is that we have a cosine of 2 theta and then a cosine of theta. That's not going to be very easy to deal with unless I translate one of them into some expression involving the other. Okay. So in this case, what I would do is I pick up my trig identity sheet and go to the double angle identities and look at an appropriate double angle identity that's going to help with this particular problem. In my case, the double angle identity that's going to help the most is that cosine of 2 times an angle is 2 cosine squared minus 1. The reason I'm going to utilize that double angle identity as opposed to one of the other double angle identities is that I already have a cosine of theta. All right, so I'm going to use the one that involves cosine of theta. Does that make sense? So essentially, I'll put parentheses, but we replace cosine of 2 theta with this. Now we can combine some like terms. 2 cosine squared of theta plus 13 times cosine of theta minus 7 is equal to 0. This one, I think, factors. Let me take a second and think about how that would factor. If it didn't factor, I just use the Pythagorean theorem, or not Pythagorean, excuse me, the quadratic formula. So let's say I didn't see that this factor. Let's pretend I didn't see that it factored. Cosine of theta, I'm treating like my variable. So I would say cosine of theta is opposite of b plus or minus the square root of b squared minus 4ac all over 2a. B in this case is 13. A in this case is 2. C in this case is -7. So we get two options for cosine. By the way, 13 squared minus 4 times 2 times -7 gives me 225. The square root of 225 is 15. So that tells me that cosine of theta is -13 plus or minus 15 divided by 4. So it gives me two equations. One of which says cosine of theta will add 15 and then divide by 4. -13 plus 15 is 2. Divided by 4 is 1/2. So 2/4 is 1/2. The other equation is cosine of theta. Now let's subtract. -13 minus 15 is -28. Divide that by 4, you get -7. If you wanted to figure that out through factoring, you could have factored as well. All right. This doesn't give you any possibilities because cosine of theta has to always be between -1 and 1. This one I can just do cosine inverse of 1/2, or I can reference the unit circle. If you did cosine inverse of 1/2, the decimal version of this is 1.05. The unit circle version of this is pi/3. Okay, so I'm going to write this theta equals pi/3. That makes sense? That gives you one of the solutions. Since we're dealing with cosine, the other solution is going to be down here. Right? Both on the right side. And I can figure that out by doing 2 pi minus pi/3. I follow that. 2 pi minus pi/3 is my other solution. And then you write decimal versions of those things in as your answer. Oh. So about 1.05, about 5.24. So that's how we deal with these types of equations. And this is why we did a lot of identity work in 7.1, 7.2, 7.3, and 7.4, so that we can be able to rewrite equations. Now, we're not going to deal with tons and tons of different options. This is about as hard as it gets in 7.5. Doing one double angle identity and then solving a quadratic. But that's how it goes. That's how we solve these equations. This one is going to be very, very similar. But if you were to do this one, I'm not going to go through this problem. I'm just going to talk like first step. If I were going to do this problem, we see a cosine of a double angle and then also a sine of theta. So in this one, what I would do is I would use the cosine of double angle, which is 1 minus 2 times sine squared. You see that? Because we have sines involved. And then you work it almost exactly like the previous problem. But this one, you'd want the double angle formula involving sine squared, because this equation already has a sine of theta in it. It's almost identical to 14, so I'm not going to go through the process of solving. Any questions about solving trig equations? And remember, when in doubt, or draw a picture when you're trying to get your second angle. For cosine, they're going to either be both on the right side of the unit circle or left side of the unit circle. For sine, either going to be both on the top side of the unit circle or the bottom side of the unit circle. For tangent, they're going to be diagonal from each other through the origin. All right. Well, now we're going to move in to the last trig chapter, which is solving triangles. Okay. We're going to have two tools to solve triangles. The first of which is called the law of sines. Now, I just want to remind you that we've already solved triangles which were right triangles. Okay. And solving a triangle means that we find all of the side lengths and find all of the angles. All of the interior angles and all of the side lengths. When we had a right triangle, we used SOHCAHTOA. We use the inverse trig functions on our calculator and the trig functions on our calculator. We use the Pythagorean theorem, a squared plus b squared equals c squared. And we use the fact that the angles of a triangle have to add up to 180 degrees. So those are the four tools we use when we have a right triangle. But it turns out SOHCAHTOA and the Pythagorean theorem only work on right triangles. So if our triangle was not a right triangle, we can't use those. Okay, we can't use SOHCAHTOA, cannot use the Pythagorean theorem on triangles which are not right triangles. Now we're going to use the same labeling convention we had with right triangles. when I say labeling convention, what I mean is we use alpha, beta, and gamma as the three angles of the triangle. We're going to still use that. And the side opposite of angle alpha we'll call A. The side opposite angle beta we call B. And the side opposite angle gamma we call C. First three letters in the Greek alphabet, first three letters in the English alphabet. So that's always going to be the convention in these next couple of sections. That's the standard convention of triangles. And it doesn't matter whether our triangle is obtuse, whether it's acute, or whether it's a right triangle. We'll still use that same convention. So the first rule that we have is called the law of sines. The first rule that we're going to add is called the law of sines. The law of sines says the ratio of sine of the angle divided by the length of the side opposite that angle is going to be constant between all three angles of the triangle. So sine of alpha over A is the same thing as sine of beta over B. It's the same thing as sine gamma over C. By the way, I'm always going to present this picture just so we remember where B is in relation to alpha, beta, and gamma. But don't assume we're always dealing with acute triangles. A lot of times we'll have obtuse triangles. I'll put the same picture there just to remind you of the labeling convention. Okay. So law of sines says this, and that should make sense because if we have a bigger angle, then the side opposite of that should be a longer side. Does that make sense? The bigger angle corresponds to the side opposite being longer. We could go through and show why this is. I'm not going to do that today. That would take time, and that's not what we need to do in this class. So we're just going to say these three ratios are all equal. And by knowing these three ratios, we've added another tool to our toolkit for solving triangles. We already knew that the three angles add up to 180 degrees. We already knew how to calculate trig functions and calculate inverse trig functions. And now we know the law of sines. And it turns out a lot of triangles are going to be able to be solved using these three tools. In fact, even right triangles can be solved by using these three tools. Let's pretend I have a right triangle. With our standard labeling convention. And I know that A is equal to 18. Alpha is equal to 30 degrees. And then the gamma is a right angle, which is 90 degrees. Let's say I wanted to solve this right triangle using law of sines and the fact that angles add up to 180 degrees and the fact that we can type in trig functions into our calculator and inverse trig functions into our calculator. So we'll use the law of sines to solve this first, in other words. Now, the first thing I would do is I would notice that beta has to be 60 degrees because the three angles have to add up to 180. So, in other words, 30 plus beta plus 90 being 180 means that beta has to be 60 degrees. So beta, that's always the easiest thing to do. If I'm given two angles, find the third by just using the fact that the three have to add to 180. That's going to be the tool that I would use regardless of whether I'm using law of sines or SOHCAHTOA or whatever. Now I want to find the value for B and the value for C, and that'll solve the triangle. Remember, solving the triangle means I get all of these. Yeah.
I don't remember if you said this, but should we be in radians or degree?
So because we're in degrees, we're using degrees. Once we start typing things in, we'll be using degrees. Okay. In these triangles, since we're given degrees, our calculator needs to be in degree mode. And so here's what I'm going to do. I'm going to utilize the law of sines with pairs of ratios. Notice that I already have the A and the alpha. So that'll be one ratio that I use. Namely, sine of alpha over A. In order to find C, I'll do sine of gamma over C is equal to sine alpha over A. Makes sense? In order to find the B, I'll do almost that identical thing. Sine of alpha over A is equal to sine of beta over B. So this one will find the C, this one I'll use to find the B. Okay. We know that alpha is 30 degrees. We know that A is 18. I know that gamma is 90 degrees. I don't know what C is, but we'll be able to find it using that equation. I would probably multiply both sides by C and then multiply both sides by 18. You'll get C times sine of 30 is equal to 18 times sine of 90. Then divide by sine of 30 on both sides. 18 times the sine of 90 divided by the sine of 30. Here's where it's important to put things into degree mode, right? We're going to type this into our calculator. Make sure your mode is in degrees. 18 sine of 90 divided by sine of 30. Should have ended up with 36 as the value of C. Does that make sense? By the way, that's because sine of 90 and sine of 30 are really nice values on that unit circle. Sine of 30 on the unit circle is a 1/2. Sine of 90 is a 1. So this is 18 times 1 over 1/2. So now we found C is 36. We'll go on to find B. very similar way, we have b times sine of 30 is equal to 18 times sine of 60. Divide both sides by sine of 30. By the way, if you wanted an exact answer, you could get that off the unit circle. Sine of 60 is √3/2. Sine of 30 is 1/2. So that just becomes a square root of 3. It's 18 times square root of 3. Which is about 31.18. By the way, you don't have to know that that's 18√3. I'm just telling you it is. You can type that in. Get that. And there, we've solved this right triangle using law of sines. Okay. Now it turns out we could have solved that same right triangle with the same initial information using our old tools like SOHCAHTOA and the Pythagorean theorem. Does that make sense? And just to show you that we get the same answers, I'm going to go back and calculate C and B using SOHCAHTOA and the Pythagorean theorem. Is that okay? All right, so I'm given A, and I know alpha is 30. So SOHCAHTOA, remember, sine of alpha is equal to the side opposite of alpha over the hypotenuse. The side opposite of alpha is A. The hypotenuse is C. So this tells us that the sine of 30 is equal to 18. A is 18. And C was our unknown. So I could have figured out C using this. C times both sides gives me C times the sine of 30 is equal to 18. And I'm saying C is 18 divided by the sine of 30. Sine of 30 is 1/2. So sure enough, I get 36 that way as well. Can I follow that? So I could have found C using SOHCAHTOA in this case because it's a right triangle. And notice that the law of sines and SOHCAHTOA give me the same value for C. Once you've found C, you can find B either using the Pythagorean theorem or you can use the cosine part. If you wanted of SOHCAHTOA, it doesn't matter. I'll use the Pythagorean theorem. So A squared plus B squared is equal to C squared. If I know A is 18, and I know C is 36, B squared is gonna be whatever 36 squared minus 18 squared is. That's 972. So B squared 972. So B is the square root of 972. Which is exactly the value we got here. Right? So what I'm saying is that not only does the law of sines work for these other triangles, but we actually could have used law of sines as opposed to SOHCAHTOA and the Pythagorean theorem in our previous work when we solved the right triangles. Okay. The advantage of law of sines is that law of sines is going to work on any triangle. So let's move on to another example where we cannot use SOHCAHTOA and we cannot use the Pythagorean theorem because I don't have a right triangle. So in this case, I'm given that we have angle of alpha as 112 degrees. Angle beta is 14 degrees. Gamma, I don't know yet, but we'll quickly find that. And then I'm given that the length of side A is 36.1. And then we don't know length of side B yet. We don't know length of side C yet. So let's solve this triangle. Using what we know. First thing, if I'm ever given two angles, I'm going to find the third using 180. Using the fact that the three add up to 180. So 112 plus 14 plus gamma have to add up to 180. Take 180 minus 112 minus 14. That's 54. So beta, or not beta, excuse me, gamma should be 54 degrees. And now we're off to the races with law of sines. I have one of the ratios I need for law of sines, the alpha and the A. I have the beta. I don't have the B, so I can use law of sines to figure out the B. I have the gamma, don't have the C, so I can use law of sines for C. So let's find the B first. To find the B, we'll use the sine of alpha over A ratio, because I'm given both of those values. Set equal to the sine of beta over B. Everybody okay with that? Just, I know one of the ratios, so set it equal to one of the unknowns. In this case, that sine of 112 degrees divided by 36.1 is equal to sine of 14 degrees divided by the unknown value of B. Multiply both sides by B. and then both sides by 36.1. And then divide by the sine of 112 degrees. Again, when you're dealing with triangles, everything's going to be in degree mode. When you're dealing with unit circle, everything will be in radian mode. So we're here using triangles. Make sure you're in degree mode. Oops. I got about 9.42 as the value of B. Anybody else get that? 9.42. Yeah. Now, by the way, for finding C, technically you could use the ratio of sine beta over B is equal to sine gamma over C. But I don't like to do that because this B was a rounded number. Since B was a rounded number, it might throw off that value for C by just a little bit because 9.42 was rounded. So what I would probably do to find C is I use the sine of alpha over A equals the sine of gamma over C. That equality, because the alpha and the A were both given to me. But again, you could do beta over B here, sine of beta over B, and you get the same C. Maybe just slightly different because of the rounding. Make sense? Yeah, I'm not going to do that, but. So sine of 112 divided by 36.1 is equal to sine of 54 divided by C. Hopefully we've done enough of these cross multiply and divide, or multiply both sides and divide. C is going to multiply. Works the same way each time. 36.1 is going to multiply. And then we're going to divide by sine of 112. By the way, if you're clever, you can just switch you can do second enter to switch the angle you're using on the top there from a 14 to a 54. So that takes less typing anyways. I ended up with 31.50 as the value of C. And now the triangle is solved. So I was given three pieces of information, the alpha, the beta, and the A. And I found the other angle and the other two sides. So now I have all three angles and all three sides of that triangle. By the way, this triangle is actually obtuse because the 112 is over 90 degrees, right? So even though on the slide, you see the picture is a cube. This angle is actually obtuse, or this triangle is obtuse with the obtuse angle being alpha. So again, don't rely on the picture other than the labeling convention there. I want you to try this one on your own. We have alpha is 42 degrees, beta is 68 degrees, and C is 36.1. Must have liked the number 36.1, I guess. That's true. See. All right. I'm gonna just gonna jump into this because people are doing really, really well getting all these things pretty well. So I'm gonna go through this pretty quickly. The first thing I would do is find gamma. Okay, I almost always do that. If I'm given two angles, that's like giving all three angles to me, right? Because we can say the three angles add up to 180. So gamma has to be 70 when you do the calculations, right? Gamma is going to be 70 when I do those calculations. Now, essentially, I have one of the ratios, the one that involves gamma and C, sine of gamma over C. And I can use that ratio to find the B, and then use that ratio to find the A. Okay. I don't know which way you like to write things. Some people like to write sine of gamma over C as the left-hand ratio, and then sine of alpha over A is the right hand when you don't know A. Other times people flip-flop that, which side you're on, it doesn't matter. But we end up with the same thing in the end. Sine 70 over 36.1 is equal to sine of 42. I'm going to do all of the moving around. A is going to be equal to 36.1 times the sine of 42 divided by the sine of 70. Okay, that's after steps there. And when I did that, I ended up with an A value, which was 25.71. So that's the value of A. And then we do the same thing for finding the beta. Once again, I like using the same ratio both times. The sine of gamma over C, because those are the given values, those haven't been rounded. If you use sine of alpha over A, because now I found A, then the A has been rounded, so you'll get something very, very close. It could just be slightly different. Again, sine of 70 over 36.1 now is equal to sine of 68 over B. By the way, notice that sine of 70 and sine of 68 are probably pretty close to each other. So B is probably going to be pretty close to 36.1, which we find that out in the next step that it is. Going to give 36.1 times the sine of 68 divided by the sine of 70. When I plug that into my calculator, I ended up with a B value of 35.62. And so now I've solved this triangle. By the way, this was an acute triangle because every angle was under 90 degrees. Any questions about that process? Okay. Now, in these first few examples, I was always given two of the angles. And so my first step was always to find the third angle and then move on from there. You can also solve triangles if you're just given one angle. In this particular case, we'll do that. So let's say I know that the value of A is 38.2, the value of B is 24.25, and alpha is 105 degrees. There's two things that are nice about this problem. All right, here we have one angle. Oh, somebody says. Of 105 degrees. The first thing that's really nice is that I'm given the alpha and the A. Okay, that gives me one of my ratios in the law of sines. Okay, I can use the law of sines to find this beta as well. Okay, I can't use it to find gamma yet or C yet, but I can use it to find the beta. Sine of 105 divided by 38.2 is equal to sine of beta divided by 24.25. And so I can utilize law of sines to find beta. So multiply both sides by 24.25. Now, so that I don't have to write so much, I'm going to get an approximate value for that number on the left, rather than having to write 24.25 times the sine of 105 divided by 38.2. That's approximately 6.132, roughly. I'll put the exact value in my calculator when I do inverse sine, but just so I don't have to write this. So essentially what I'm saying is that this beta is going to be the inverse sine of this number. So I do inverse sine of my answer. And I get 37.82. Now, here's the other really nice thing about this particular problem. Okay. The 37.82 was this angle. Okay. There's actually another angle on the unit circle that has sine value of 0.6131 and blah, blah, blah. That other angle is the supplementary angle. You guys know what supplementary means? Supplementary means add to 180. over here. That's 142.8 or 0.18 degrees. Okay. So the other option for beta was 180 minus 37.82. That other option obviously cannot work. I understand why it can't work. I can't have an angle that's 142 degrees and another angle that's 105 degrees. That's too much. Well over 180. Okay. So this is also nice for the second reason that there's only one option for my beta. And that option is the 37.82 degrees. Okay with that? Now that I have alpha and beta, I can find gamma in a fairly straightforward manner. Gamma, in this case, had to be 37.18. So you guys got 37.18. Very close to what beta is. That's interesting. Didn't expect that. But now that I have gamma, now I can find the C using log sines as well. So sine, again, I like to use the given as much as I can. Sine of 105 divided by 38.2 is equal to sine of 37.18 divided by the unknown value of C that I don't have. So that's sine of alpha over A equals sine of gamma over C. And then just like we've been solving, 38.2 times the sine, 37.18 divided by sine 1.5. Then just plug that in my calculator. I get the C value to be about 23.90. And now we've solved the triangle. Is that all right? Again, this was a nice case because of two properties. One property is we had one ratio given to us, the sine of alpha over A. That was given to us. The other nice thing was that when we looked at the supplementary angle, the supplementary angle didn't work. And so we only had one option for triangle that this could have ended up being. That doesn't always happen. There are times, like in this example, where things don't work out quite as nice. This is nice because of one reason and not quite as nice because of another. So we're given side lengths B and C. B is 14.5. C is 12.95. And we're given angle gamma is 36 degrees. And we want to solve the triangle. Well, the nice part of this problem is that we have one ratio for the law of sines. That's a nice thing. Okay. We have that the sine of gamma over C, that'll be a constant. So I'll find beta using the law of sines. Sine gamma over C is equal to sine beta over B. Or again, it doesn't matter which order you write that in, whether the beta and B are on the left or whether on the right. So we have sine of 36 divided by C of 12.95 is sine of beta, don't know beta yet, divided by 14.5, that's B. Oh. So I get this. $14.5 times sine of 36 divided by 12.95 becomes about 0.6581. So one beta that we get is simply the sine inverse of that 0.6581, blah, blah, blah. That is 41.16. Okay, let's get that. 41.16 sine inverse. Good.
If I got 41.15, could I add the one after EA?
Oh, yeah, I'm putting second answer in it.
Okay.
So when I did the second answer, that's what I got. Rounded. If you did round this to 2 decimals, you could get something that's too far off that Moodle wouldn't recognize it. So I would just put second answer or do sine and inverse of this whole mess. You can type this in, sine inverse of this whole thing. Then you'll all be on the same beta. Now that is an angle here in the first quadrant. It turns out that the supplementary angle to this one is 138.84. Notice that if our angle gamma is 36 degrees, both of these will create legitimate triangles. Does that make sense? So what we have here is a situation where these three given numbers actually could create two different triangles. One with an acute angle of beta, and the other with an obtuse angle for beta. So what I'm going to do is I'm going to, in this class, do both options. If you run across this in your homework, it may say use the acute angle only. All right, so there'll only be one option. Or it may say use the obtuse angle only or something like that. Or maybe it'll only give one option. To write down, use the smaller acute angle option, something. But we're going to actually have two different triangles for these given three pieces of information. By the way, now we're going to do the same thing in both. We're going to say I have gamma, beta, find alpha by using the fact that the three angles add up to 180 degrees. For this one, alpha would be 102.84. And then I'll go through this one as well. For that one, I get 5.16 degrees as my alpha. And then in both cases, I solve the same way. All right. Sine of 102.84 over A is equal to sine of, I'll use the non-rounded numbers, 36 over 12.95. So, I should probably wrote it backwards, but. So on that top triangle, the first one, I take 12.95 times the sine of 102.84 and divide it by the sine of 36. So for that top triangle, I get an A of 21.48. And if I did the same thing in the bottom triangle, I'd use just 5.16 as my alpha instead of 102.84. Same concept though. And I get an A value of 1.98. So I get two options in this case for triangles. And that is something that can happen when you're only given one of the angles. All right? When you're only given one angle, that can happen because sometimes both the inverse sine and also the supplement of the inverse sine both work. But like we saw in our previous example, there are times when the supplement won't work because it'll add to over 180. Does that make sense? So there are times when the supplement won't work because it adds to over 180. But again, I'll point out in both of these cases, we started out with a ratio of law of sines, which was nice, right? That was a nice thing. And this is what I've said. There are times when you can get multiple triangles if you're given one angle and two sides. Because we have this obtuse versus acute option for my angle beta in both cases. All right. That only happens when we have one angle and two sides. And it only happens with these angles. I wouldn't say, yeah, it only can happen with an angle less than 90 degrees as the given angle, because then the supplement won't work. I'm not going to go through example 6, but what I will say is when you go through example 6, you're given two sides and an angle. You're given one ratio for your law of sines, the alpha and the A. It turns out when you find gamma, because you'll find gamma first since you're given a C. If you go to find gamma, only one of the options of gamma is going to work. So only one of the options of gamma, the supplementary option of gamma, is going to add up with 45 to be over 180. That makes sense. So I won't do example 6 because of that. And just as a little, how do I say, what's going on graphically or what's going on with the figure, all right? What's happening is I have a angle. Let's draw the angle over here. Which angle was I given? I was given gamma. All right, so I'm given an angle, but I don't know the length of this side. I do know the length of this side. Which one was I given? B. So B. And I do know the length of C. Okay. I'm trying to think of I'm trying to get something that's straight line that I don't have. I don't know if I have a good straight line. That's okay. Maybe I'll use my pen, I guess. No, it's too short. I'll use a piece of paper. Okay? That's what I'm gonna do. Figure it out, yeah. Okay. All right. So we're given the length of B. We're also given a length for C. That length for C can rotate. All right, and that's right out there. You gotta be about the same size as B. C was slightly less than B. There we go. Slightly less than B. So length of C can rotate. I'm gonna try to do this. So if the length of C is the side, what we're saying is what triangle has start point here and end point here? I can rotate this down until I get this type of triangle. And the C could be there. Or if I rotate this up and around, I could intersect this side here. I get that? And so we get two triangles, two options for my triangle. For the alpha, the B, and the C. I didn't draw that very good, but these are the two triangles. One where the beta is an obtuse angle. One where the beta is an acute angle. Make sense? So that's the picture that's happening. It's this rotation. And we're saying we have to intersect that side. There's 2 points, we intersect that side. And so we get two triangles with that given length. All right. So we do have scenarios which give us two triangles. Most of the ones that I'm going to give you probably are going to have one option for triangle, and it'll be the acute version of whatever we find. Now, so far, I've always given numerical values that work out and make sense. All right. There are certain triples that won't make sense. Okay. And that can be illustrated in this next problem. So there are certain values, if I give you two sides and an angle, or if I give you two angles and a side, there are certain values that just can't happen. It's actually two sides and an angle again. So imagine that you know A is 203.8 and alpha is 98 degrees. And then it says C is 302.7. Long story short, this triple of values won't create a triangle. I'll talk about why that is numerically, and then why that is intuitively as well. Let's do the numerical problem first. So we start trying to solve. We do sine of alpha over A is equal to sine of gamma over C. I'm going to multiply both sides by 302.7. Okay. Now, just calculate that left-hand side. 302.7 times the sine of 98 degrees divided by 203.8 gives you a 1.47-ish equaling sine of gamma. If I do sine inverse of both sides, I'm going to get an error because sine always has to be a value between -1 and +1. Okay. So numerically, we know that gamma does not exist. And therefore, there's no triangle that exists in this case with those given lengths and measurements. That's the numerical approach. You solve it, you see gamma does not exist, can't get a gamma that works there. The intuitive approach is the following. We had side length A be 203.8 and side length C be 302.7. Which of those angles, therefore, has to be bigger? C, that gamma, the one associated with C, right? Well, if this is bigger than 98 degrees, then these two angles already add up to something that's more than 180. And so that doesn't work because you can't. This side length should have been the biggest side length if we had wanted a legitimate triangle. That work? So there are some triples that just don't exist, don't give you a triangle. Like this one, like this example. You don't have to see that. As you start solving, that'll become apparent because your angle won't exist. But there you go. Now, the last thing I wanted to say on law of sines is that law of sines is a great tool, but with the trig functions, with angles of triangles adding up to 180, and with law of sines, there are scenarios which I'm given 3 pieces of information, and I can't move on using those 3 tools. Okay. The example that I'll give right now, just to show you, is that if I have B as 21.1 and alpha as 34 degrees and C as 19.7, I can't find a missing angle because I need 2 angles in order to find a third using that 3 angles add up to 180. Inverse trig functions aren't going to work. And also law of sines doesn't work because I don't have any of the ratios alone. That makes sense? In my law of sines, if I do sine of alpha over A is equal to sine of beta over B, there's two unknowns. Sine of alpha over A is equal to gamma. Sine of gamma over C, there's two unknowns. Sine of beta over B is equal to sine of gamma over C, there's two unknowns. So law of sines doesn't actually allow me to figure out what A, beta, or gamma is in this scenario. But there is a triangle with these three measurements. If you think about it, alpha is going to be 34 degrees, so we know how to measure that. B is going to be 21.1. C is going to be 19.7. So I know that the triangle looks like this, right? It's very much defined. I just can't use the law of sines to figure out this length or the other two angles. So we do have a triangle there, a unique triangle that we can find. But we need another tool. Okay. And as you can see, that's going to happen whenever you have one piece from each ratio. If you have two sides and an angle in the third ratio, then we need another tool. Or if I have all three sides, then I'm going to need another tool as well. Does that make sense? If I know all three side lengths, then you only have one piece in each of the ratios. So we need another tool. And the nice thing is, we have another tool. And that other tool is called the law of cosines. And with the law of cosines, and the fact that the angles of a triangle add up to 180 degrees, and the fact that I know how to use trig functions and inverse trig functions, and my law of sines tools, it turns out I can solve any triangle. Right, as long as it's legitimate and I can actually, you don't get a does not exist scenario. So we have already seen law of sines. Law of cosines looks very different. There's actually three law of cosines rules. One for cosine of alpha, one for cosine of beta, one for cosine of gamma. And what you'll see is this. The side opposite the angle. Let's do the first one. So like a squared, a is opposite alpha. So we get a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of alpha. Notice that on the left-hand side, it's always the side length opposite the angle. On the right-hand side, it's the sides that are adjacent to the angle. The two sides that are adjacent to the angle. So this is the law of cosines. Now, it's probably the most complicated tool. So we want to use this sparingly. We can minimize, if we can use law of sines is an easier tool to use. So I use this as sparingly as I can. And I'm gonna use it to find either one side or one angle, depending on the scenario. And then I'll use my other tools to find everything else. So let's solve the triangle that we were just given, that we couldn't solve in the previous section, where B is length 21.1, alpha is 34 degrees, and C is 19.7. So because I know alpha is 34 degrees, I'm going to use the law of cosines with angle alpha in it. That means I'm going to take a squared, set that equal to b squared plus c squared minus 2bc, multiplied times the cosine of alpha. In this case, B, I know is 21.1. C, I know is 19.7. Again, B is 21.1. C is 19.7. And cosine of alpha is cosine of 34 degrees. Takes up some space, this law of cosines. That right-hand side is something I can just type into my calculator. I ended up with a square being about 144.0879, blah, 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 right? And I'm just going to take a square root of that number. Second answer. So square root of my answer. And that gives me an A value of about 12.0. 12.00, rounding it to 2 decimal places. Anybody else get that? Once I know the value for A, then I say, good, I don't have to use the law of cosines anymore. Now I can jump to my other tools to find the beta and the gamma. My other tool mostly being the law of sines. Everybody okay with that? So let's do that. Let's say sine of alpha over A is equal to sine of beta over B. I know alpha is 34 degrees. Now I know that A is 12. Excuse me. Find that deal. I got about 79.50 as my beta. Could we have used the supplementary angle there? Supplementary would be 100.5. That work? Let's keep it for now. By the way, cosine, this was well defined. There wasn't any other A we could have gotten, right? A was completely well defined. Let's figure out what gamma is if we use 79.5, right? If we use 79.5, 34 degrees plus 79.5 plus gamma would be equal to 180. So gamma in that case would have been 66.5. If I would have used the supplementary angle, gamma would have been 45.5. Now it seems like at this stage, the way I've solved it, both options may be correct at this stage. But the sign of each of these is different. These are not supplementary angles here for gamma. So one of them is going to work, one of them is not going to work. Okay. I want you to calculate the sine of 66.5 over 19.7. Then calculate the sine of 45.5 divided by 19.7. And then calculate the sine of 34 over 12. One of these is going to match with this one. One of these is not. They follow that? I would have ended up with this. So which one is the correct one? Well, it's the 66.5 version, which means the 79.5 version is the correct beta. Does that make sense? So in this case, the supplementary angle did not work because it gave me a gamma which was inconsistent. All right. The other way you could have solved this is at this final step, instead of solving this by just angles adding to 180, you could have used the law of sines. And it turns out the law of sines only gives you this and its supplement, which is not going to work. So, that's me. So we're just using the regular angle beta. That's not the supplementary angle that we found. Any questions about this? The key component is law of cosines. All right. Key component that we're dealing with is law of cosines. I want you to try this one on your own. Use the law of cosines to find C. Over here. And then after you found C, find the alpha and the beta. Yeah. I'm gonna use one more again. All right. By the way, the general convention for this is that you round to 2 decimal places on your angles and on your side lengths. Okay, so on the homework and on the test, we'll round to 2 decimal places on this. If I'm given the gamma, then I have to use the law of cosines, which involves the gamma. On that one, c squared is equal to a squared plus b squared minus 2ab times cosine of gamma. So in this case, c squared would be 7.6 squared plus 8.2 squared minus 2 times 7.6 times 8.2 times the cosine of 74 degrees. The right-hand side gives you 90 point something or other. Lots of stuff. 64455,997. And it goes on from there. But we take a square root of both sides, and that would tell me my C is 9.52, rounded to 2 decimal places. Now we can use that. Now that we have this, we have a ratio for the law of sines, and I can use that to either find my beta or my alpha. Okay. I'll find alpha first. Should I find alpha or should I find beta first? I'll find alpha first. Sine of alpha over 7.6 is equal to sine of 74 degrees over 9.52. Multiply both sides by 7.6. Whatever this thing is, I'll take the inverse sine of it to find alpha. I did that, but I got alpha as about 50.12 degrees. Okay. Now, if I look at the supplementary angle of that, I get 129, and 129 and 74 are going to add up to too much. Does that make sense? So I can eliminate the supplementary option right now. which you probably figured you could. Now, the quickest way to get alpha, or excuse me, I misspoke there. I wrote the 50.12 in the wrong spot. 50.12 should be the alpha. Quickest way to get the beta is by angles add up to 180 degrees. You could have also gotten the beta by using sine of beta over 8.2, and you'd come up with the same thing. So, as always, choose the easiest tool. 50.12 plus beta plus 74 equals 180. So take 180 minus 50.12 minus 74. I got 55.88 degrees as the value of beta. That makes sense? So, easiest tool gives 55.88. I'm going to show you real quick something. You don't have to write this down. But if we did find the beta using the law of sines, I would have done that. Point 8. 7, 9, 7. I would have ended up with 55.89 degrees. Okay. And then I would have gotten an alpha of 50.11 degrees after that. So you notice the reason for that is because the C is a rounded value. Okay. And when you put this into the law of sines with the beta, you get it slightly different than when you put it in with the law of sines and the alpha. You get slightly different measurements. Both of those will be counted in Moodle, all right? So if you found beta using law of sines, or if you found beta using angles adding up to 180, both of those will be fine to type into Moodle. So you don't have to worry about that. It'll be very close either way. Again, that 9.52 being a rounded number throws things off just a hair. Okay. All right. Yeah, both are counted, but fine to go. Now, the last scenario in which law of cosines is needed is the scenario in which I'm given 3 side lengths and no angles. So in this case, I'm given that A is 32.9, B is 16.8, and C is 23.6. So I'm given 3 side lengths, no angles. once again, if you think about how this has to work, we have to have a triangle with these measurements. There is a triangle out there that is going to work, and there's only one triangle that will work. The only time you get two is in that scenario we worked out earlier. So in a case like this, what we're going to do is we're going to find one angle first. It does not matter which angle you find. You can find the gamma, you can find the beta, or you can find the alpha. Doesn't matter. I'm going to find the gamma in this case, just because I already have this formula written down from the previous exam. If you wanted to use the formula with cosine of alpha, you could use that. If you wanted to use the formula with cosine of beta, you could use that. I'm going to use cosine of gamma, and that's going to force the c squared to be on the left-hand side. In my case, that's 23.6 squared. On the right-hand side, I'm going to get 32.9 squared plus 16.8 squared minus 2 times 32.9 times 16.8 times the cosine of gamma. Now there's a lot of numbers, but they aren't just numbers over here. So 23.6 squared, 556.96. I'm going to combine these two values. 32.9 squared plus 16.8 squared is 1364.65. And then this whole thing, 2 times 32.9 times 16.8, that's just the coefficient of cosine. So 2 times 32.9 times 16.8, that's 1105.44. And now I just have to solve for cosine of gamma. I would subtract 1364.65 from both sides. That's negative 807.69 is equal to negative 1105.44 times the cosine of gamma. Divide both sides by negative 1105.44. That gives 0.73065, blah, 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 is the cosine of gamma. Everybody see where I'm getting that? Dividing both sides by 1105.44. And then I take cosine inverse of that answer. that's about 43.06 degrees as my gamma. Now, I claim that I don't have to worry about supplementary angles here. Does everybody understand why I don't have to worry about supplementary angles here? The reason I don't have to worry about supplementary angles in the cosine case is because when I solve for cosine, one of my angles was either in the first or second quadrant. The other angle was in the fourth or third quadrant. So for instance, in this case, I get 43.06. That's an angle here. The one that matches with cosine is either a negative angle or more than 180, whichever way you want to see that. So negative angle in a triangle doesn't work. An angle that's more than 180 in a triangle that's not going to work either. Everybody follow that? Since it's the right-left pair on cosine, I really only need the 43.06. So that's a long explanation to say we don't have to check supplementary angles on cosines. That's not one of those. Cosine is well defined between 0 and 180. Cosine inverse, excuse me. And again, you have something between 0 and 180. So there you go. So now I have gamma and C, and now I can use my law of sines to find beta, or I can use my law of sines to find alpha. I think I'll use to find, well, which one do you want to find first? Beta? Let's find beta first. Okay. Sine beta divided by 16.8 is equal to sine of 43.06 divided by 23.6. I got that beta would have to be 29.08. By the way, once again, I don't have to check the supplementary angle here for two reasons. The obvious reason is I know beta is not my largest angle because it's associated with a smaller side opposite it. So it can't be over 90 degrees. Does that make sense? So based on very quick, easy reasoning, beta can't be over 90 degrees because if beta was over 90 degrees, it'd be the biggest angle. And that doesn't make sense. Side opposite has to be. Beta is not the biggest angle because the side opposite is not the biggest side. That work? You could have also calculated the supplementary angle and it turns out if you calculate the supplementary angle, the supplementary angle is 150.92. That together with 43.06 would give you something bigger than 180 degrees. So numerically, it doesn't work either. So, but we knew going in it wasn't going to be over 90 degrees anyways. And then once we have solved for beta, then we can say alpha plus 29.08 plus 43.06 has to be 180. So we take 180 minus 29.08 minus 43.06. And then alpha would have had to been the 107.86 angle. Is that right? By the way, seeing some of these tricks, like, oh yeah, that's gonna have to be a smaller angle than, alpha was gonna have to be a bigger angle than beta. So finding beta first, I knew beta was gonna be a small angle rather than something over 90 degrees. Those types of things can save you some time. If I solved alpha using the law of sines, it turns out I'd have to use a supplementary angle, the 107.86. The other angle I would have gotten would be about 72.14. And that one would not have worked. Again, main part of this is just being able to find the gamma here. Right. Now I know we only did one example. There is another example in the notes. If you wanted to try that other example, I can give you the answer to that. But I just want to reiterate, when you're solving triangles, we have all of these tools. We have angles of triangle add up to 180 degrees. We have inverse trig functions. We have trig functions. We have law of sines, law of cosines. Not every triangle is going to need all those tools. Law of cosines is my most complicated equation. So that's the one I try to avoid if I can. Angles adding up to 180, that's the one I want to use as soon as I can use it, right? That's the easiest version to use. So for instance, if we were given this, I have alpha, beta, and C. The first thing I'm going to do is angles add up to 180. And then I'm going to use the law of sines because that's the easier thing to use compared to law of cosines. You could use law of cosines to find A if you really wanted to, but it'd be more work than it's worth. Now, I won't go through the law of sines connection to right triangles, but in this last little bit, I do want to mention the connection for law of cosines and right triangles. All right. And here's all I'm going to do. I'm going to look at our law of cosines when gamma is 90 degrees. What is the cosine of 90 degrees? On the unit circle, that's straight up, right? X value is 0 when things are pointing straight up. So cosine of 90 degrees is 0. What's that going to turn this into? Pythagorean theorem. Yeah, this turns that into the Pythagorean theorem. Right? In fact, some people say the Pythagorean theorem comes from law of cosines with gamma is 90 degrees. So the law of cosines is just the, how do I say, shifted version of the Pythagorean theorem. And without going into it, it turns out the law of sines is actually SOHCAHTOA and reverse, or not reverse, excuse me, adjusted. Okay, in right triangles, the law of sines becomes SOHCAHTOA. Does that make sense? If you take the sine of alpha over A equaling the sine of gamma over C, well, if gamma is 90 degrees, sine is 1. And that says sine of alpha is the side opposite over the hypotenuse if we have a right triangle. Makes sense. And you can do the same thing for beta, and the sine of beta is the same thing as the cosine of alpha because they're complementary angles. And then you can do it, you can put those together to find tangent. Is that right? Okay. Well, that ends section 8.2, the law of cosines. Obviously, we went the whole time today. Make sure that the homework gets done by Friday at 5. And then, excuse me, and then make sure the test gets done Sunday at 5 or earlier. Okay? All right, if you do have any questions, let me know. Other than that, I'll see you on